So how long until the Earth gets swallowed by a solar flare? How long do we have?
Well, we do have a pretty active sunspot that's going to be rotating to view today, and it's been blasting off some storms, like 2 big coronal mass ejections the past 5 days or so. So we could have the Earth swallowed up with a big solar storm anytime in the next 7 days, 10 days. I think it's going to happen, but we don't know. The sunspot could diminish. It could get bigger and more active.
I see my X feed is littered with these types of posts that there's a sunspot, there's a solar flare, there's a double solar flare, there's all these things happening, these coronal mass ejections that are gonna cause a cataclysm or something like this, and nothing ever happens.
Yeah, there's this interesting, because I cover this in my videos and I talk about it, and it's just an interest of mine, because originally I was focused on the geology and then the geophysics of the Earth, and naturally I had to start studying the space environment to understand what was happening here to a better degree. And so as a result, I learned about this, and I make a video saying, hey guys, we have a solar storm coming in. This is the forecast. Let's say we do see it launch, right? It's like guarantee we're going to get hit. We have a G3 storm. A lot of people will be like, oh, here he is calling for the end of the world again. It's like, well, guys, I never said that. It's just like this, we have a solar storm coming in. But there's something about the mix of it being epic in scale, because it is a massive explosion on the sun, which is many times the size of the Earth. So it's this fundamentally epic in scale, paired with also a lack of education as to these things. And even adding a third of some people taking these events and then twisting them into a doomsday narrative, and having done that for a long time, that creates this convergence of people thinking that the moment there's a solar flare, we're all doomed. But that is like, we could have what we call a super flare, and we don't know how that would affect the Earth. But in terms of, is that going to happen tomorrow? Or we would need a gigantic sunspot, like unbelievably large, and we would have clear optics on that, and we're not seeing that right now, but it could happen.
What is the biggest solar event that has impacted the Earth the most, like in recorded history, that you're aware of?
Yeah, there was a really big, this is kind of a complex question, but in 1859, there was a Carrington event. That was a really big solar flare, and coronal mass ejection, impact, and a really strong geomagnetic storm. We've had other Carrington level solar storm impacts since then. 1872, 1921. We kind of got lucky in 1972. It didn't have the right magnetic field configuration, but it was strong enough to set off these landmines at Vietnam.
Whoa.
Yes, that's an interesting one, because they just deployed these landmines off the coast of Vietnam. Then we had this super fast solar storm impact, but again, the magnetic field wasn't conducive for a really strong, like, magnetic storm where the magnetic field's going nuts. But it's still enough of a shock impact just because of the velocity and the density that these sea mines like went off. That was 1971. We had a close miss in 2012. Some people know about that. But those are, let's say, a Carrington level event. There's solar storm impacts that are less than that, like what happened in May 2024. That was a big solar storm impact, actually multiple in a row, that triggered what's known as the Mother's Day storm, or the Gannon storm. This is May 10th to the 12th of 2024. During the solar maximum, that was big, but that's quite a bit weaker than like a Carrington level impact. But if you go back, we have these isotope records where we see these radioisotopes jump up dramatically, like carbon and beryllium. And we don't exactly know what caused those to go up. It could be a solar storm impact. That's the most likely candidate, but it could be cosmic in origin. They're called Miyake events. And so if it is solar in origin, then that's classified as a super flare. And that is about 10 times bigger in scale and stronger in scale in general, if not even like up to 2 orders of magnitude stronger, 100 times stronger. So those would be the largest. But in terms of us having like really hard data on that, we don't. So 774, 775 AD, we had a really powerful Miyake event. You can go back through the record. We had some really powerful ones. They kind of come in clusters, it seems. But going further back, there was also a really powerful Miyake event that we're starting to get good data on right around the border of the Younger Dryas event. So that's kind of interesting because it like lines up pretty closely with when that cataclysm went down. And there's some people that talk about there being a solar trigger for the Younger Dryas, and then other people talk about comet trigger, or maybe it's just orbital cycles and Milankovitch cycles and such.
Right.
But I think it was a convergence of factors. But yeah, the point is that we can see a small solar storm come in and let's say trigger a G3 geomagnetic storm. That's a moderate to strong one. We can see a Carrington impact, how that would affect technology and like satellites and power grids and more. Nowadays, we don't really know. Then we could have a super flare, and that certainly wouldn't be good.
What would happen during a super flare?
Well, we don't really know because these power systems and tech and everything has been hardened quite a bit, but I do have a feeling that if we had a super flare, like we had a really big super flare, we'd probably lose a lot of satellites.
So it'd be like a giant EMP.
That's exactly what it is. It comes in so fast that not only is there a massive electromagnetic pulse, which can cause a lot of satellites to undergo what's known as deep dielectric charging. They can short circuit. You also get the upper atmosphere of the Earth to actually energize and raise up. And so the density of the atmosphere increases in some aspects. And so these satellites in low Earth orbit all of a sudden encounter more drag. And as a result of that, they will often lose their altitude and burn up.
Whoa.
And so we have quite a bit of data there in terms of Starlink, in terms of there being just regular solar storm impacts. And then we see some Starlinks are falling out at rates greater than maybe Elon would hope for. But they're always launching more and more up. So they're kind of replenishing. But if you had a super flare, like a real legit super flare directly aimed at Earth, impacted, I think probably the majority of satellites would go down. We don't know, but that's probably what would happen because it'd be so far beyond what we've experienced. We already see we already see the effects of what's been happening. And it can be pretty severe with some of these smaller solar storms. And then power grids, I think there'll certainly be blackouts globally, but maybe not one massive global blackout, but isolated, maybe larger. It's hard to say, but it would be a huge black swan event.
What happened? Can you lay out what happened during the Carrington event? Like how bad were we affected by that?
We weren't that affected technologically because we only had telegraph lines.
This was in the 1700s, 1800s.
1859.
1859, yeah.
And that was the first solar flare that was observed on record. Carrington, this British chap, was looking at the sun and he saw it start to flare. And then he ran to go grab like an aid or something to tell them. And he actually missed seeing the peak of the event, like that 1 minute where it's really going nuts. Then he came back. This is what they've kind of been able to reconstruct historically. Yeah. But that he saw effectively the flare. They estimated it was up to like a X65 flare. There's different categorizations. It's logarithmic. So you go from, let's say, C to M to X. Those are the three highest. That's a 10X jump each time. And if you have an X65, then that's 65 times more than X1. So a huge jump. That's some of the estimates are in that zone. It could have been less. We don't know. We don't have the modern tools of characterizing these events back then as we do now.
Sure.
But in less than 24 hours, I think it's about 16 hours or so, maybe less than that. It wasn't more than 12. We had this impact come in, and all of a sudden telegraph stations were catching fire and lines were like melting. And there were some reports where they disconnected the power and they were still able to operate their machines. Because as that solar storm hits, you have a whole bunch of high energy particles. This is really if we really zoom out and look at the Earth as a whole, we have to be very thankful that we have a magnetic field because that protects us from high energy particles from space, cosmic or solar. And if we didn't have that, things would not be good. If you want to colonize the solar system, you got to figure that out because most planets don't have a magnetic field, or moons, for example.
Right.
I mean, Jupiter, Saturn, Uranus, Neptune, they have magnetic fields, but they also generate their own super high energy particles. So the radiation's
Mars has a magnetic field, doesn't it?
Just crustal anomalies. No global globally generated magnetic field.
Oh, whoa.
Yeah. There's ideas that you could put a big magnet in front of Mars and keep it in line with the sun and basically create an artificial magnetosphere, but I'm not so
Is that one of the biggest issues with colonizing Mars?
it'd be a big one. Yeah, it'd be a big one because Mars is still close to the sun. There's also like the fact that I don't think a lot of us realize just how close the Earth is to the sun.
Right.
At 1 astronomical unit, we think Mars or Venus and Mercury are closer, and they are. But Jupiter's at 5. That's actually still very close. Saturn's at 10. Uranus is at 20. Neptune's at 30 astronomical units. It drops off quite a bit when you go that far out.
Mm-hmm.
But when you're at 1 AU, you're getting like really walloped. So we have a strong magnetic field on Earth. It's actually very strong if you look at kind of the solar system scale. Mercury's field is 1/100th the strength. It's very, very minor. Venus doesn't have a magnetic field. Mars doesn't have one.
Why do we have such a strong magnetic field?
Because we have a lot of internal processes within the planet. Our planet is very active and alive, whereas Mars seems to be dead geologically for the most part. They did register like a magnitude 4.6 earthquake on Mars in 2022, I believe. So that's pretty big. But, we get like magnitude 9.5s and probably larger. But we have a lot of active processes, and there's a lot of the research in geophysics across time has been trying to figure out how Earth has been able to maintain its energy and heat for billions of years. And so it's kind of like Earth in many ways is a macrocosm of life. We don't really know how it keeps going and replicating, but it does. Mm-hmm. And that generates a magnetic field. These geodynamo processes, and I think there's probably some other factors involved as well.
Interesting. What's the deal with this South Atlantic anomaly? Are you familiar with that?
Yeah.
There's some sort of like hole in the electric field there, like somewhere in the Atlantic, like Southern Atlantic Ocean.
Yeah. Off the coast of Brazil. An easy way to think about it, this isn't exactly precise, but if you think about Rio de Janeiro, that's effectively the center of the magnetic anomaly. It's the largest magnetic anomaly.
Oh, interesting. So you can find an image of it, Steve, or like a illustration.
Yeah. And so this is where the magnetic field on the Earth is the weakest, and quite a bit so. It has been growing, it has been weakening at a rate that is measurable in the human time frame of years to decades. So it's pretty significant. If you look at the history of magnetic anomalies, there is quite a rich observational record of positive and negative magnetic anomalies that are transitory. So they exist for, let's say, 200 years, 300 years.
Oh, interesting.
So we don't fully know how long this magnetic anomaly is there. And the physics of it's pretty complex. The general idea is that there are these patches of reverse flux that are deeper within the Earth, near the core mantle boundary. The core is where the magnetic field is generated for the most part. I also think that there may be some magnetic field generation in the mantle and further up, but that's a whole different conversation. But if you have this patch of reverse flux that is canceling out the positive flux, let's say, like the positive magnetic field, and then this one's coming in with the, let's say, negative magnetic field, they're just going to equalize. Mm-hmm. And so the overall field strength would be greatly reduced as a result. And so that's what we see with the South Atlantic anomaly. And as a result of that magnetic field being so much weaker, the strongest magnetic field strength on the planet is Antarctica with the South Magnetic Pole.
Right.
Or rather, the magnetic pole in the southern hemisphere. It's actually a positive magnetic pole. But regardless, that's about 67,000 nanotesla, which is
how much again?
67,000 nanotesla.
67,000 at the South Pole.
Yeah, or we could say it's a 0.67 Gauss. There's different, varies of values that you can use. Mm-hmm. But at the South Atlantic anomaly, it goes down to like 22,000 nanotesla or 0.22 Gauss. That's like a third as much. It's really quite weak. So you get a lot of cosmic rays that come in there. That affects satellites.
That eats up like most of South America.
Yeah, that's a reason why they're all dancing and going crazy down there.
You think that's it?
I do, actually, yeah. First time I went to Brazil, I was like, it is definitely different down here.
Well, how long has that anomaly been there?
That we don't know. We have some data. So the first good
When
magnetic.
were we able to first start measuring it?
Yeah, exactly. So we first started getting relative magnetic field measurements either in the late 1600s or certainly in the early 1700s. And that would be where they take a magnetic field measurement in their location. This is mostly by ship, right? And then they would track it as they, navigated across the globe, but it'd be fixed at location. Then we developed absolute magnetic field measurements around the middle 1800s. It's like 1830 or so. And since then, we deployed more and more of these stations to be able to get good magnetic field measurements across time that are absolute in scale. So everywhere can be compared to each other. Whereas with the relative stuff, it's hard to piece it together. Also, across history, we've had really good coverage of the northern hemisphere versus the southern hemisphere, because most of the land mass is in the north, most of the population's in the north, and most of the ocean surveys were in the north. So our maps that we reconstructed from the historic data for the 1700s and even earlier have very limited coverage where the South Atlantic anomaly is. There is evidence that it existed during this time, but you can't really go really beyond that in terms of saying it. Some people think it's been around for like hundreds of thousands to millions of years. I'm not so sure about that, because we've seen positive flux magnetic anomalies that have popped up suddenly and then gone away. The Levantine Basin, Western Europe, Hawaii, Japan, a lot of these places have experienced where the magnetic field suddenly strengthened dramatically. The field strength, as I said, at its strongest right now, Antarctica, 67,000 nanotesla. There's evidence from the Levantine Basin where it was like 120, 130,000 nanotesla. But that was just like a transitory pulse.
Where is that?
It's like Israel and Lebanon and that whole area.
Whoa.
And the magnetic field was stronger back 1000 AD and then also 1000 BC. Those are the two rough dates where the magnetic field overall was stronger.
How do we know?
That can be tracked a few different ways. You can measure the remnant magnetization of, let's say, like a lava flow.
Oh.
Because these are lava flows. Magma has a lot of metallic minerals in it, like magnetite, titanomagnetite. And so they will, upon cooling, lock in the direction and strength of the magnetic field. But we also have limited lava flows. Like we don't have global coverage.
Right.
We don't have a lava flow at every single point on the planet. So you can do a lot with that.
Interesting.
That's probably the most useful. You can also record the remnant magnetization and the intensity, direction, all that stuff from just magnetite or other magnetic minerals that settle out in sedimentary layers. It'll be very, very low density, you could say, because you have a whole bunch of, let's say, like quartz settling out, which isn't magnetic. But if you do a drill through, let's say, a lake floor, and you get that tube of sediment, then you can kind of chronicle the magnetic field that way. So that's another one.
It's like a proxy, basically, for what was going on with the magnetic field.
That's another good one to add in. And then the one that I think is the coolest is anytime you fire up pottery, you're also generating effectively a magnetic signature at the time that the pottery cooled at. Because what happens, there's something known as a Curie point, whereas if something heats up, these magnetic minerals, if they heat up beyond about 650 Celsius, I believe it is, they lose their magnetization. So if they recorded a prior magnetic field measurement, if you heat them up, they lose it, and then they cool down, they'll lock in whatever the new one is at the time of, let's say for the pottery, time that it was fired and cooled down. So we have archaeointensity data from all these pottery sherds that we find across the world. And so we have really good coverage of the magnetic field measurements, for example, the Levantine, because there was so much, pottery and civilization across the years. And
so back to that Southern Atlantic anomaly, how does that affect us? Like, is there any sort of implications on that to the rest of the Earth or that area of the world?
So the implications right now are that if satellites fly through that area, they often get hit with more high energy cosmic particles, or during a really intense solar storm impact, more high energy particles from the sun.
We'll get through there.
Yeah, and that can affect the electronics and such. But in general, it doesn't seem to be that big of an issue from that aspect. In terms of the biology, that's really interesting. Something we don't know much about, but the more you learn about bioelectricity and everything, we see how we're connected to all these energies. I mean, we're in resonance with the earth across the board. So
you're really getting multidisciplinary now.
yeah, so there's a lot of interesting stuff there, but we don't have much like data on that, you could say, in terms of like the direct impact, let's say, on the South Atlantic anomaly and, heart attacks in Brazil.
Sure.
That would be interesting data. We see a connection between heart attacks and geomagnetic storms and other things like cardiovascular issues, but there's some like really precise, detailed stuff that we just don't have data on.
A lot of crazy UFO stories from Brazil. We just had a crazy podcast about that last week.
I had a dream where this is like maybe 18 months ago, 24 months ago, where the UFOs, the aliens announced themselves in Brazil.
Oh, God.
And I woke up, I was like, that makes sense.
Oh, dear.
There you go, peeps.
There you go, folks.
Yeah, it was odd, but I was like, that makes sense. I could see them being like, hey, well, this is no different than what we already have because it's already so culturally diverse there.
Oh, my God. Yeah.
But in regards to so that's with the Atlantic anomaly, like the real world implications now, not really too crazy. But if it continues to weaken, if it continues to expand, then it could be a sign that we're undergoing a geomagnetic excursion, which if that was to continue could translate into a full geomagnetic reversal where the magnetic field actually flips.
Oh, Jesus.
And there's a kind of few ways of tracking that. The three main ways, I guess you could say, would be what's the overall field strength for the Earth? And that needs to drop to a certain level, it seems, for the excursion to really kick off. And right now we're well above that threshold that's been identified, but doesn't mean we can't continue to weaken. The magnetic field has been weakening since our high 1000 AD, about 1,000 years ago. So it's gone down since then, but still historically very strong. But if it continues to weaken, then we have to kind of be mindful of that. But this is like geologic time. It's unlikely to occur within our lifetime. But I also am like, hey, who the heck knows, right? And then there's also where are the actual magnetic poles? Because we have the North and South Pole. But if they start to really move like well outside of their historic areas of, let's say, the Arctic and Antarctic circles, then it's like, okay, we should be mindful of this. And
well, they do move like pretty quick. They move like a couple feet a year. Is that right, Steve? We looked at this recently.
Oh, way faster than that right now.
Oh, really?
Right now, the magnetic pole in the Northern Hemisphere is moving about 40 kilometers per year.
40 kilometers per year?
Yeah.
Whoa.
Yeah, so that's moving really quickly. And there's some ideas as to why, because there's some changing magnetic field dynamics between North America and Siberia, which is interesting. But that is a quick movement. Right now, the magnetic pole in the Northern Hemisphere is almost exactly on top of the actual North Pole. So while it's been moving quickly, it's almost perfectly in the Arctic Circle in terms of its positioning. Whereas the magnetic pole in the Southern Hemisphere, during the same time frame, has moved away from the true South Pole, like the rotation axis, to be just slightly outside of the Antarctic Circle, but it's only moving about 10 kilometers per year, and it's doing it tangent to the Antarctic Circle. Whereas the magnetic pole in the Northern Hemisphere is kind of moving towards the lower latitude zones, like it's moving towards Siberia. It's still off the coast in the Arctic Circle, where there's all the sea ice. Over Gokul Ridge, but it's starting to, some people are worried about it actually moving into Siberia and then moving down like over India, for example.
The magnetic pole.
Yeah. There's some ideas that, if it accelerates even more, that it could be there pretty quickly. And that, if it accelerated enough, it could. But it's been deaccelerating over the past 10 years roughly.
Okay.
Because it accelerated up to 60 kilometers per year. Now it's down to 40. But still very fast. But the magnetic poles moving are also an indication of what's happening at the magnetic field. And then you can measure specific components of the magnetic field because you have like a regular bar magnet. It's called a dipole. So there's two poles to it, the north and south. Earth's magnetic field is not exactly a dipole. It's about 95% dipole, but there's these higher order modes. So like a quadrupole, which is interesting because it brings the magnetic field in at the equator as well, not just looping like this from north to south, but a quadrupole actually brings it in at the equator as well. It's 4 lobes. That makes up a good portion of Earth's magnetic field as well. That's a good graphic.
Which one?
That one or the other one in white, but
come on.
to the right, that one right there. That's a good one as well.
Oh, cool.
And so what happens during excursions is the dipole field strength diminishes greatly and actually goes away. And what we're left with, this is what the evidence suggests, is that then we're left with the quadrupole, the octopoles, the higher order modes, which make up only 5-10% of the overall strength. Those don't seem to change. Then the dipole reemerges in the reverse polarity. And with an excursion, it aborts. So it may get all the way to that flip, but then it reemerges with the polarity it had. Whereas with a full reversal, it will actually take on this new polarity. But that dipole field needs to go away for that to occur. And so then all you're left with is a quadrupole. And that would have really interesting implications in terms of space weather, because now you have the magnetic cusp also not only in the high latitude zones, but also at the equator. So anywhere along the equator, you get blasted with solar energy at that moment in time. Whereas right now it's funneled mostly to the Arctic Circle, the Antarctic Circle. That's why they see crazy aurora up in Northern Europe, for example.
Yeah.
Or we don't really get aurora down the South Atlantic anomaly, but we get a lot of those high energy particles because the magnetic field is weak there. This is a really great graphic. So
does this tie into this seems like it could be connected to the, what's it called? The Van Allen radiation belts?
Yeah.
So the Van Allen radiation belts are directly tied to the magnetosphere of the Earth and like solar wind, right?
Yeah. So we have our sun, which is, we kind of don't know what it is inside, but we know it's surrounded by this sheath of plasma, super high energy plasma. And then we have our interplanetary environment. So that radiates out from the sun, and we have an overall heliosphere, which is made up of plasma, that the sun is just always pumping out plasma. It creates this larger magnetic field and also this plasmasphere, which we call the heliosphere. Effectively, every magnetic field contains plasma within it. Because if you look at Jupiter, for example, it has a very strong magnetic field. It also has a really powerful plasmasphere. So we don't call them Van Allen belts there. I guess they could be Jupiter's Van Allen belts or Jupiter's radiation belts, but the radiation environment within Jupiter's magnetic field are insane. It's like really, really high.
Really?
It's way more intense than Earth.
Why is that?
Jupiter's magnetic field is
just to have a stronger magnetic field.
It's like 5 or 10 times stronger than Earth's. It's super, super strong. So you get huge amounts. And then you also have, like, for example, here it's showing Io. Io is a volcanic planet. It's blasting stuff into...
is it a moon?
Yeah. Volcanic moon that's blasting stuff into orbit around Jupiter, which then gets ionized. But every magnetic field effectively also has a plastosphere. And what happens is that they are particle accelerators. These magnetic fields accelerate particles at speeds near the speed of light. So they go relativistic. And as a result, they contain a tremendous amount of energy, because the faster they travel, the more energy they have if the mass stays the same. And it's not linear. It's like exponential in how that goes up. So, and Jupiter's is actually so powerful that we observe what's known as Jovian flux in our interplanetary environment. So every 13 months, we enter into this arrangement with Jupiter magnetically where we're connected, and we get this burst of Jovian electrons, which we call Jovian flux. And it's a very specific energy spectrum, which is how we identified it to be in Jupiter and not solar in origin. But we orbit around the sun, of course, 12 months. Jupiter does 12 years. And so it's moved 1/12 of its distance in 1 year. So that's why it's 13 months. Because as we orbit around, it's moved 1/12. So we need another month to catch up to that magnetic configuration. But we see particle acceleration with Jupiter and massive amounts of radiation there. And we have that here on Earth too with our radiation belts. And so our magnetic field is also accelerating these particles, and it's being fed and replenished all the time by these solar storm impacts or solar wind that connects to Earth in a preferential way, like a conducive way, will recharge our plastosphere. And then that plasma often will precipitate down into our planet and drive these geomagnetic storms. So it's a really complex system.
Yeah.
It gets wild because then how does that affect the telluric currents, and how does that affect maybe the geodynamo, and at what time scale are you considering? Is it just the hourly, daily time scale, or you think how does maybe space weather affect the geodynamo over thousands of years? These are all open questions in many ways.
Getting back to what you were just explaining about the North Magnetic Pole shifting down into Siberia or like India, what would happen if that happened?
Well, the main thing to be aware of as it relates to the movement of the magnetic poles is that if Earth's so I'm sure that there's a wide range of possibility that's happened over Earth's geologic time frame. We have quite limited data on that. In terms of modern data, it's almost non-existent compared to the geologic time frame. So in general, though, if the magnetic poles were to move well outside their normal ranges, then that's an indication that the field strength is diminishing, and that magnetic pole really doesn't become that great of a measure of what's happening anymore because the overall field is weakening in general. The dipole field is going away. So you're going to have a lot of places where you could say the magnetic field is going in vertically. Like there'll probably be multiple magnetic poles that could pop up. But when the dipole field is strong, you have two clear magnetic cusps and two clear places where the magnetic field is going in vertically to the Earth.
I see.
But as the magnetic field diminishes, that can kind of just get thrown into flux. So it's a useful measure, but in some aspect, if we're really undergoing an excursion, it kind of becomes less useful because they can really float around really quickly because the whole field itself is so chaotic and turbulent. Like the sun undergoes a magnetic flip about every 12 years. That's the solar cycle. And during that time, there's tons of places on the sun where the magnetic field is kind of slicing back in, and
really?
Multiple
so it wouldn't
magnetic
make
poles.
it wouldn't really affect it. We wouldn't really notice it.
I mean, we would definitely be able to track this and it would affect us, but it's not I guess what I'm getting at is it's not the best way to track what's happening with the magnetic field, like just the location of these magnetic cusps. It's not the best way. I think probably better is to track the dipole to quadrupole ratio, and then also the overall field strength. But as that pole moves, you're going to have energy flux moving with that cusp.
What's up with all the fear, like all the crazy hypotheses and theories I hear online about like the pole flip could reset humanity?
Yeah.
Like everyone says that this could be like a cataclysm.
Yeah. So during an excursion, so like the Lechamp excursion, the field strength went down to like 5% of what it is now for about 100 years, roughly. That's about the time frame and about the field strength. And that would mean that if you're out and about, you're receiving a huge amount of cosmic radiation. And that's not going to be good. Also, if there is this connection between grand solar minimums and geomagnetic excursions, during a grand solar minimum, you're not getting these big super flares or solar storms or whatever, just solar flares in general, but still pumping out most of its energy, which is most of the irradiation from the sun is infrared, visible, and then also ultraviolet. Right. And ultraviolet, can break DNA bonds and, single strand breaks, double strand breaks, mutations, all that. So if you had a geomagnetic excursion like the Lechamp, which is when the Neanderthals died out, and the field strength's at 5%, you're letting in a ton more cosmic radiation. The sun is still pelting you with UV light as well. So it's going to be fairly traumatic. We had a megafauna extinction in Australia at that time. Big animals can't hide from this stuff. Whereas
when are we talking again?
This is about 42,000 years ago.
Oh, okay.
42, 44,000. It's roughly in that zone. I think that is why those cave systems in Turkey exist, if you're aware of those. Because
You're talking about the cave they found underneath that house?
I'm not sure about the house, but they have this elaborate cave system in Turkey that's thousands of years old. I don't remember the specific name.
So you can find it, Steve.
Yeah. But a lot of people have different ideas as to why that exists. But if you have a geomagnetic excursion, the cosmic ray, like you can feel this stuff, right? When the sun's really active and you go out, or just going from, let's say, Nebraska down to Mexico, you're like, wow, I can really feel the sun on my skin.
Darren Kuyu? Talking about Darren Kuyu? Darren Kuyu is the one they found under that house. They dug under the house and they found this giant cave system.
It was like a giant man-made anthill.
Yeah, exactly.
Yeah, that's
is that what you're talking about?
Yeah.
Okay.
And so I think that could exist specifically during these sort of events where you would literally feel the energy hitting you and it would not be pleasant. And over time, you would see health effects from that. And so it makes sense that you would take shelter underground.
Right.
And this is a long period of time too.
How long do you think?
It's like 100 years. And that's just where it's at its absolute minimum for the field strength. It's going to be about 1,000 years of where the field's very weak. So it's a long enough time for that to make sense. Whereas some of the ideas that people have is that it's a big solar storm, like a super flare coming in, and they run to the caves. But that's like a 3-day thing. And you don't have a heads up on that. It's not something that okay, this is clearly a factor. Let's work around it.
So when you're saying this could have lasted 100 years, what you're saying is it could have been different day to day. There could be days where it was safe to walk around. This wasn't just a consistent 100-year period of super intense radiation hitting the Earth.
No,
right?
It would be.
Oh, it would be constant.
In general, yeah.
Okay.
Yeah. I mean, it's hard to say without being there and getting the data. But
sure. I mean, we're speculating wildly, but
in general, for the Champ excursion, we see that the field strength dramatically weakened, and so that'd be factored. Same amount of UV light if you did have all these grand solar minimums.
Yeah.
And then a ton more cosmic radiation, which is going to cause mutations and more. So something like that makes perfect sense, and it's a long enough time period for that to be a feasible engineering project that makes sense to devote resources to. It's not just why would you have that for a super flare you don't even know is coming?
Yeah, well, I never understood. I've heard the explanations that these things were to protect people against floods, but why would you want an underground cave if you're getting flooded, right? I never really understood that. And they claim that the rock doors could have blocked the water, but I don't know if I buy that. I don't understand how this underground Darren Kuyu, how you could survive underneath that when there's tons of flood water surging above you. It would just go down there, I would think.
I mean, I haven't been there. I like to go to these sites so I can speak about them.
This is not accurate. I don't think this is accurate, Steve. I don't think that's what it looks like.
Oh, yeah, that's Cappadocia.
Oh, okay. Yeah, something different. That's volcanic caves, also in Turkey? Whoa. Christian churches inside these caves? Whoa.
Hollowed ground.
That's wild. Is that real? Is that for real? Huh.
Tuft, volcanic tuft is easy to carve out.
Yeah.
So that makes sense.
Hold that thought. I got to take a leak real quick. We'll be right back. There's so many possibilities for what could have caused extinction events in the past. Is it comets? Is it volcanoes? Is it solar flares? Is it all of the above? Who knows? But it's fun to speculate. They're some of these structures. This had to have been. Why else would they dig these underground cities unless it was to escape something, right? And also, to live without sunlight for an extended period of time has got to be super unhealthy. You would imagine that there wouldn't be long-term health effects living underground.
There has to be some health reason that outweighs that, I would think.
Exactly.
I don't think it's climate.
That's a very, very well stated.
I don't think it's climate because, it gets hot there, but we don't see people in Turkey living in these underground cave systems right now.
No.
So, and actually back 5, 6, 7,000 years ago, it was probably quite a bit nicer there, right?
Really?
Well, I mean, you had the back during the Ice Age, Turkey was probably a great place to live because it was quite a bit colder. It's still a very nice place, but it gets hot there during the summer, or like Egypt, for example. But 6,000 years ago, Sahara was still green.
Right.
So in terms of it being like absolute scorching desert, and that's people go there to live in cooler conditions, I mean, maybe. I think it's probably doing multiple things at once.
Have you ever seen those? A couple years ago, we had Randall Carlson in here showing us this graph of all of the ups and downs the climate has been through for millennia, and it's like there's these insane. He was using it to illustrate like the Younger Dryas, the time period of the Younger Dryas, how like we went from super cold to super hot, and there was these huge spikes like at the beginning, at the end of the Younger Dryas, and all this stuff, and like how the temperature has been just up and down forever. And he was showing like during, I believe, I mean, it's been a while. I don't know if this is, I'm recalling it correctly, but I believe he was showing like during the medieval period, it was like super warm, like even warmer than it is now. Are you familiar with this?
Yeah, the medieval warm period.
Right.
Yeah.
And how much, do you know how much warmer it was like than it is now? See, you can find that graph, Steve.
It was not
Super
homogeneous. So a lot of the warming was concentrated in places like Iceland, Northern Europe, Greenland. It was much warmer there, like much warmer than it is in the current day. That's why it was easy for them to go and settle those locations. So it wasn't the warming was really concentrated in some of these high latitude zones. It was not homogeneous around the planet, but there was a distinct warming event. Interesting work that was, and some connections put forward by my buddy Max Raymond. I have a podcast with him on my channel, but he looked at the record of supernova explosions and also the medieval warm period. And there's like a pretty tight correlation in time between us seeing these supernovas, which if we're seeing it, we're getting some energy from that. Just how much, what type, what's the significance, it's hard to say.
Right.
But there is this connection in time because we had 3 big supernovas that we saw at the early, I guess, 10th, 11th, 12th, 13th century. Like the famous one's 1054 AD. But then we see this distinct warming that occurred immediately after that.
And we're in a cooling period now, right?
Well, overall, the Earth is warming. But in general, I think the safest thing that you could say is that our climate and weather is becoming more volatile. So we're seeing...
Really?
Yeah. I mean, for example, in December, there was a huge heat anomaly over the United States. Though, like the Yukon, Canada, Alaska, that was excluded. They had a huge cold snap there. Also, like Maine was quite a bit cold. But like here and also Texas and a lot of the heartland, the U.S., had tons of temperature records broken for December. Meanwhile, Moscow, like right now, has had one of the biggest like polar blizzard cyclones of all time. And the snow is piled up like crazy. So overall global temperatures are going up. The Arctic is warming like 3-4 times faster than other spots. But in general, there's just more volatility across the board. That's my take home, because what we see is sometimes we get these sudden changes in temperature. So like we could be on this warming, but I wouldn't be surprised if all of a sudden we have a cold snap that comes in, because we're in an interglacial right now. That doesn't seem to be the trend, but trends sometimes suddenly reverse. But if we want to be prepared for the future and just kind of understand where we're going, then the bigger thing to be aware of in my mind is that we're just seeing increased volatility, stronger storms, more frequent, in locations that we typically wouldn't have storms, at least with our recent record. I guess one of the big things I really want people to be mindful of is that a lot of our data doesn't go back that far. I mean, let's say like 1850, right? For a lot of our climate records, a lot of our geologic records, like the solar records. I mean, the space age started in like the 50s. So a lot of that space data only goes back to like 1950, really. So we have in our seismic data for earthquakes, we have some data going further back because we found the fault trace in the slip and we can reconstruct it. But in terms of like good seismic data, like 1900, these data sets are almost meaningless in a geologic sense. I mean, they're super useful and we get good information out of them, but 10,000 years of data or 50,000 years of data, that's still just a drop in the bucket for the Earth, which is millions and millions and millions, billions of years old. So I think it's important not to draw too many definitive conclusions as to these are the only possibilities that exist for the Earth.
One of the craziest things to me is it's so hard to know what's really going on with the Earth's climate and all this whole topic. It's so hard to know what's going on because it comes with so much political baggage.
Yeah.
Like there's nobody who has a take on the climate that is not attached to their political ideology or like what they label themselves out.
Except maybe me.
Yeah, right.
That's because I see it. My first principle is I want to understand what's happening. So, and well, politics, I mean, the whole thing's stupid. So like I could care less about either side, but I just want to understand what's happening. So we know that this, like our sun, the star in our system is the main driver of climate. Because if that was all of a sudden to go away, Earth would all of a sudden be very cold, dark. It would not be a fun place, right? It would change everything. We're close to the sun. We receive a lot of light radiation from the sun. That's our total solar radiance. It's about 1,370 watts per square meter of energy coming in. That changes across the solar cycle. Total solar radiance doesn't change that much. We can say it goes from like 1,370 to 1,374 in terms of total solar radiance because most of that energy is infrared, optical, or visual light, and then also UV.
Right.
But we get distinct changes in X-ray light, extreme ultraviolet light. Also, radio frequency light goes up quite a bit in intensity during solar maximum versus solar minimum. But that's the main driver of the climate. Then there's what's happening with the Earth and her own changes, let's say like water vapor in the atmosphere and the hydrological cycle. And then there's what are we doing to alter those systems with anthropogenic greenhouse gases and stuff. And for some reason, some people are like, oh, it's just CO2 and our sun doesn't affect the climate at all. And then other people are like, oh, CO2 does nothing. It's just the sun. It's like, it's a combination of all these factors.
Right.
And they're probably going to vary in their significance at times too.
Sure. Of course, we contribute to the carbon in the atmosphere, like the CO2. Of course, we contribute to it. Is it enough to literally like create a new ice age? Or not a new ice age, but like to warm up the Earth and melt the ice caps to where like it's going to change the Earth? Like I don't know. But it's just, like I said, it's just so volatile and there's no middle ground in this kind of stuff. And it's hard to like hear a nuanced take on what's really happening. I see articles all the time that the ice caps are growing, right? Like the ice sheets are getting bigger right now. And, depending on what website you go to, you can find a different scientific take on what's happening.
Well, yeah, I mean, December would be a good example because some outlets were probably reporting about the huge cold snap that hit the Yukon and parts of the U.S. Meanwhile, other outlets would only cover the huge warming trend that hit, the heartland and most of the United States. And,
right.
Europe's a whole different place, but other parts of the globe. But yeah, it's unfortunate that
look at this. NASA satellites show Antarctica has gained ice despite rising global temperatures. How is that possible? An abrupt change in Antarctica has caused the continent to gain ice, but this increase documented in NASA satellite data is a temporary anomaly rather than an indication that global warming has reversed, scientists say. Yeah.
Yeah, oceanic circulation.
The problem with all this shit is that it's just so entangled with money.
Yeah.
There's all these little financial entanglements in science that make it screwy, which sucks. It's with everything.
Yeah, money's kind of a crazy thing, which is, I'm not perfect and, I've made mistakes and I'm sure in 10 years I'll look back at certain things I've said or thoughts I had and as new data comes out, I'll be like, okay, this is my new revised idea on this. But I do like the fact that I've taken myself out of any kind of constricting influence by just kind of becoming independent and, by educating others publicly online, people like that enough that it keeps me afloat. And great. I think we need more independent voices. I think we need more independent data collection networks. Like one of my long-term life goals at this moment in time is to create like a global observatory for geophysical and solar data and more. So we're not reliant just on government organizations. Like one of your questions earlier is where do I track this stuff? And we get a lot of great data feeds from NASA and NOAA and other space and government organizations. But there's often political interest there and conflicts of interest. And I mean, there's some things that just sometimes you're like, why are they not speaking the truth about this? Or why are they not addressing this thing that occurred?
Why are they assassinating plasma physicists?
Weird stuff, dude. Yeah, the MIT.
Dude, how crazy is that? I saw some stories about that. I don't know what to think. There's just so many crazy takes on that.
Yeah, how much have you been tracking the 3i Atlas story? Because I've been doing a ton of research there.
I haven't really. I heard that. So Avi was telling us that it was like December 16th was when it was going to be closest to Earth, right? And that was the time that we were going to have like the best shot at it to figure out what it was. And I haven't heard anything about it since. Have you been tracking it?
Yeah, I mean, it popped into view, June 1st or July 1st, we first caught our glimpse of 3i Atlas. And then I jumped on that pretty quick because it was interesting. But yeah, it became this bifurcated, kind of oppositional warfare between there's 4 million draconian soldiers on this thing versus it's just a comet. Meanwhile, our definition of a comet is built off of just I don't know, like 50, 100 years of observations.
Sure.
And some historic eyewitness viewing, but space is so much more vast and dynamic than we know. So to call everything just a comet is a little short-sighted. Because comets have a fairly low bulk density. It's mostly ice and these volatile gases that are turned into ice, like CO2 ice and methane ice. And, they start to vaporize effectively as they get close to the sun. But one of the key things is that they're kind of fluffy and they have a low density to them. 3i Atlas has shown some signatures that it's not just that. It's had these tightly collimated jets. So that sunward facing tail is one of those. It extends out quite a bit and it's not just like a shotgun super diffuse. It's, fairly tightly collimated. And we've also seen jets come off other locations of it. And I mean, we've seen this like jets before with comets and such, but 3i Atlas certainly is different. And one of the things that we see in space is that you often get jets when there is a central body that's rotating, that's magnetized. That seems to be a key factor in the production of jets. So if you have a rotating central body and it's magnetic, has an endogenous magnetic field, that can create the structure to collimate these flows of plasma. So we see that certain galaxies, you have the centrally rotating core of the galaxy. It's highly magnetic because it's made up of all these stars and whatever, maybe black holes. You have these jets coming off of that. Supernovas, same thing. So there's some evidence that this is kind of what I think, based on my research, that 3i Atlas may have a level of magnetization to it. And there's even some processes that can occur in interstellar space due to the processing of cosmic rays that would generate magnetite in situ, which is magnetic. And so if 3i Atlas does have a strong magnetic field and it is rotating, we know it's rotating, but how fast is still kind of open. They say it's like 16 hours. I think it actually may be rotating faster than that, but there's no hard data on that. But there's really not that much data on this thing in general.
Right. We haven't been observing these interstellar objects for very long. Like this is the third one, right?
Yeah. And since it came in super fast, like how did it get that speed, right? Its trajectory through the solar system, while very unusual in terms of it being aligned with the ecliptic plane, passing close to Mars, and then passing close to Jupiter in March, that is just kind of a random thing. Unless it is, intelligent by nature, like it was planned. But there's always weird trajectories that you can draw up. So the speed, though, is key. It's traveling super fast. What gave it that velocity, or at least relative velocity to us?
Well, if it was interstellar, right? you could, how would we know? Like we don't know how fast interstellar objects typically go, do we? I mean, we have 3 to measure. So
Exactly.
like, if it's coming from some other star system, it would have more time to gain momentum, maybe.
Or how is ejected. Yeah. So there's a lot of different ideas, but I mean, one idea is that you could have maybe a planet just get through tidal forces just totally fractured apart. It passes too close to a very, like, let's say like a red dwarf that just rips the planet asunder. And if it's Earth, Earth has a significant inner core. It's made up of iron and also nickel, and it's magnetic, like all this stuff. You could have a chunk of that perhaps fly off. And if that's going at fast enough speed and it has magnetization already, you don't just lose that.
Right.
There has to be a process for that to get lost. Then that could, if this thing is compositionally different, and that would also have a much higher bulk density, like the bulk density of that would be like 8 grams per centimeter cubed, whereas water is 1. A comet bulk density is roughly about 1 gram per centimeter cubed. It could be dramatically different. We haven't landed a probe on it. We've landed probes on comets before. We've done some missions like the Rosetta mission, but we didn't do that with 3i Atlas because it kind of came out of the blue too quick, but
Going super fast.
So there's a lot of unknowns, but yeah, just to throw a label of comet on it, I think is premature. So we call it a interstellar object.
Right.
But then also to take the word of, I think these people are amazing in the spiritual community, like channelers and psychics and all that. I think there's a lot of cool stuff there. But just to take the word of a channeler who's like, there's 4 million draconians there, and that's 100% your perspective going forward. I'm like, I don't know. That's also the exact same as this person saying it's just a comet, just on the other side. And so I made a lot of videos about exploring all the different perspectives, and guaranteed every video I made, some people were, thrashing me online for saying, I can't believe you think it's a comet. Meanwhile, I'm calling it an interstellar object. And other people saying, I can't believe you're not, recognizing that's 100% alien filled with draconian soldiers.
Yeah.
I'm like, guys, I'm just presenting all the different ideas in the middle, interstellar object, but people see what they want to see.
So, was NASA able to get like a super detailed image of it on December 16th when it came as close to the Earth as it was going to get? Are you aware of that? And then what were we able to analyze from that?
So there were weird things that happened. I mean, we had this government shutdown in October.
And they weren't releasing the images that was like the Mars orbiter or whatever.
Yeah, and see, Loeb, he really pumped up this Mars Reconnaissance Orbiter imagery. Like if you, and he's also edited a lot of his blog posts.
Who? Avi?
Loeb.
Has he?
Yeah, so because there are certain things that he said, which, I mean, rightfully he edited them because they turned out to not be, I think he got a little carried away at times. One of them was with the Mars rover. It has a mass cam that looks at basically the sky every single night in general. And there were some weird things that we were seeing. And one of the images is Phobos, but the internet community took it and said, that's 3i Atlas. And he posted
It was a moon?
Yeah. And so he posted that. And then he went back and edited the article later, which is fine. It's good to be, accurate rather than leaving.
But does he
up.
leave like a footnote saying that he made an edit?
I don't know about that. But going from basically probably August through September, he was talking big about the Mars Reconnaissance Orbiter, the HiRISE camera. We'll get our highest resolution look. We'll be able to, focus in on that nucleus, see exactly what it looks like. And then when it actually got the imagery, he's like, "Oh, I'm not surprised. It doesn't look that great." But there's this thing with public communication, whereas if you're communicating, you have to expect that people are going to sometimes take that information. Maybe they don't hear your future updates. You have to be very clear and nuanced with your communication, I feel like. And the imagery we got from NASA was the highest resolution imagery we got. But there was a lot of improper communication with it because these amateur astronomers, which were doing amazing work, getting imagery of 3i Atlas, they're looking at the whole thing. The tail, the coma, you're not seeing the nucleus because the coma is so thick, this envelope of gas, dust, plasma, everything. They're seeing the whole thing. NASA was zoomed in on the coma. And so that's why it looked like a blurry blob.
Right.
Because you're not seeing the tail or anything. You're punched in on the coma.
Yeah.
But they did kind of a poor job at telling people about this because, they were very adamant that it's just a comet, and they had this whole press conference, and, they did some weird things too, which I kind of questioning why they behaved a certain way.
Who, NASA?
Yeah, there's some oddities across the board. But in general, they did give us our highest resolution, but people also, they want certain things. So they wanted this to be, some starship. And when the imagery came out that it wasn't.
Was that the image, Steve?
Yeah, so I got two sets of images for you. So this one right here is the Hawaii telescope, Subaru telescope in Hawaii that took this on December 13th.
Yep.
And it's just this fuzzy ball.
Okay.
That's great. And then here's a more cooler one.
Whoa.
From, I'm guessing, one of the space stations.
Oh, this is a G3 Atlas, though.
Oh, this is
it's a different one.
G3?
It's 2024, October 1st.
That's so cool.
Oh, it says 2025 here. Okay, well, then never mind.
But that's what a typical comet looks like.
Right.
This one's super cool.
Wow. Well, yeah, so that one's got a typical tail of a comet, right?
That's R2 Swan.
But then
It's a lemon.
this is 3i.
There's no tail on this one, really.
Now, that one's probably pretty punched in. We're seeing it's only 10 arc seconds across. So that's a pretty high resolution look at the coma. And the thing is that these telescopes, that's what they do. They don't take good wide view pictures of space. If they want to get that, they have to take multiple pictures and then create a mosaic and stitch them all together.
Right.
And if they're only focused on understanding the coma and the nucleus, we don't need to see the tail. But NASA probably should have taken some time to get those wide angle views because that's what everyone wanted. And they're accusing them of all this crazy stuff. And there are some weird things happening. So it's not helping them by them not doing the work, you could say. But to answer your question, Hubble started taking a lot of imagery of 3i Atlas up to this moment in time. So starting November, December, and up now, they've been taking a lot of imagery of it. But still in the raw state, hasn't been processed except by a few amateur astronomers. They're processing the Hubble data, which is showing these jets go off, which is some of that observational evidence that maybe 3i Atlas is magnetized. And the Rosetta mission by ESA, the European Space Agency, when they flew a probe around this comet that they were tracking, they actually picked up a magnetic field around it that typically had a strength of 30 to 50 nanotesla. But when a solar storm hit it, it went up to 300 nanotesla. So a comet, a traditional, regular comet, can already have a pretty significant induced magnetic field. So you can imagine if the object itself, let's say 3i Atlas, has remnant magnetization to it, and it is spinning fairly rapidly, then you could create the conditions for these sort of astrophysical jets. And what we see across the scales is that there is a fractal nature to reality in the universe. And so if we're seeing astrophysical jets at the galactic scale and at the interstellar scale and at sometimes the actual, a single star exploding at the supernova scale, why can't we have jets with maybe a smaller object? So there's a lot of interesting things there.
Yeah, it's wild.
It's a big mystery. I don't know what it is. I think it's a unique.
It's exiting our solar system now, right? It's on its way out.
Yeah, it's leaving now, and it would have to do something dramatic for that to change because it's moving so quickly. About 65, 66 kilometers per second right now, roughly. It's sped up with its closest approach to the sun, its perihelion, to 68. Because gravity, is actually accelerating as it gets closer to the sun. And then that deviates its course a little bit.
Right. It's got an arc.
The fact that it only deviated a little bit shows you just how fast it's going.
Yeah.
Because most comets, they'll have a huge deviation in their orbit. But 3i Atlas was just it wasn't even 45 degrees. It was probably 15, 20 degrees. One of the big things in astrophysics is why is there this matter-antimatter imbalance? Why we only see matter, but we're not seeing antimatter? That just kind of strikes me strange that if you have these things generated in equal amounts, and that's what's stipulated with the Big Bang, how could one overcome the other in the first place? And they say there's some some quantum particle physics that explains that, but I don't know. My spidey sense goes off.
What is antimatter?
It's effectively the opposite of matter, but you wouldn't really be able to tell what antimatter is until annihilation occurred. Because when matter and antimatter come into contact, they just immediately create energy. So there's nothing left over other than just pure energy. It's the most energetic thing that we know of. Like a matter-antimatter collision is incredibly energetic.
So what was his take on the Big Bang?
Well, he didn't think the Big Bang is what happened. His idea was that there was more of a steady state to the universe. And to keep it really simple is that you have a matter-antimatter balance, and we don't know exactly at what level you start to encounter antimatter. I mean, it gets kind of wild, his ideas. But for example, our sun and our solar system could be matter. We don't know if Sirius is antimatter. Sirius A, Sirius B, or Alpha Centauri and Proxima Centauri. We don't know if those stars are matter or not. They could be antimatter. Because the light, there's not.
We can see them, right?
Yeah, there's not light and anti-light though. So
right.
So they're just generating light. There's no way we can tell until we were actually kind of get close enough to sample. But maybe they are matter, and instead you get these interstellar pockets of matter and antimatter. So it's a star cluster that's all antimatter, and another star cluster nearby that's matter. Or maybe it's even at the galactic scale that you have this division. He was even talking about there being antimatter chunks in the sun that generate solar flares, and it gets kind of wild. But at the boundary between matter and antimatter, you're going to have annihilation, which is an extremely energetic process, which generates gamma rays. And as a result of that collision, there's going to be a natural repulsion between the two. And so they're going to spread out. And then a lot of that galactic flux, the cosmic, the gamma rays will get absorbed into other mediums and stuff. So it may be kind of hard to detect. But that could explain some of the cosmic flux that we see in the environment. But his idea was that gravity would bring these different pockets of matter and antimatter together over time. And then annihilation would become a process that outweighs them in force, which then pushes them apart again, which then would diminish the amount of annihilation that's occurring because these boundary layers that exist, because they're now far enough apart. There's a low enough flux of matter hitting antimatter. This cushion that exists is now very low energy, that then gravity starts to bring them back in together. And now you get more annihilation, and you get this rhythmic pulsing to the universe across time.
Oh, interesting.
And so the universe could be, let's say, 50% smaller at one point, I don't know, like 10 billion years ago, let's say.
Yeah.
And then it expands out and eventually contracts and expands. It contracts, expands. And that was his, in general, to keep it really simple, that was his idea as to the universe. And, we're not really going to be able to get good data on that until, we actually get probes well beyond our solar system. Voyager 1 and 2 are still basically right at the edge of our heliosphere. So we haven't gone to Alpha Centauri and, set foot down and be like, oh, what the heck is this? So it's a lot of, I just like his mindset of build off of what we have and then go forward with that. And we'll get a lot more answers as to antimatter as these particle accelerators are able to produce more and more of it. And we can do more testing of it, you could say, but we don't have any direct measurements of it.
Yeah, it's interesting. Did you see that there was a recent post that I found, and there was a paper attached to it where I think it was the James Webb detected some galaxies or something that were like, they were so big, they were like super massive galaxies that they would have to have been like, it like throws off the whole timeline of the consensus of like the Big Bang. Did you see that?
Yeah, they just keep pushing things back. And
yeah,
I just personally, see
if you can find that paper, Steve, the James Webb supermassive galaxy discovery.
The big thing with the Big Bang is there's this cosmic background microwave radiation.
Exactly, yes.
And they kind of like, okay, well, this is here and we have this inflation to the universe, then let's just wind the clock back and it comes to a singularity. But If there's other dynamics, like for example, this pulsing that we discussed, you could wind it back, but then maybe it doesn't actually go all the way to a singularity. Like maybe you should stop winding the volume, the clock back at a certain point because it actually doesn't go beyond that. So there's like a lot of assumptions that have been made. But I don't know. I just explore with an open mind. I'm just a young chap who's interested in this.
Yeah.
I feel like I have a fairly good spidey sense, and I think it's good to ask questions.
Is this it? This is March 2025.
This is the announcement.
Oh, okay. Is this on? This is on the NASA website. Oh, yeah,
NASA,
NASA.gov. So let's see what the summary of the top says. Using a unique infrared sensitivity of NASA's James Webb Space Telescope, researchers can examine ancient galaxies to probe secrets of the early universe. Now, an international team of astronomers has identified bright hydrogen emissions from a galaxy in an unexpectedly early time in universe history. The surprise finding is challenging researchers to explain how this light could have pierced the thick fog of neutral hydrogen and filled space at that time. The James Webb Telescope discovered an incredibly distant galaxy, JADES GSZ. How do they come up with these names? Z13-1, observed to exist just 330 million years after the Big Bang. In images taken by Webb's NIRCam near-infrared camera as part of James Webb Space Telescope Advanced Deep Extragalactic Survey, researchers used the galaxy's brightness in different infrared filters to estimate its redshift. Right, its redshift, which measures. See, I had a dude on here recently. I was trying to show this to me, and he was trying to tell me this was like some crock pseudoscience, but this is on NASA's website. So this thing is so old and so big, they have to push the timeline back.
Yeah,
because of the redshift.
I mean, they do incredible work. And if you look through some of the, like this book that I'm reading right now by Hans Oliven, it was co-published with NASA, but it's from like the 80s. So there was a much more open-minded spirit of investigation back in the 50s, 60s, 70s, 80s. And there have been a variety of people like Freeman Frund, who, looked into rock circuits and the electromagnetic dynamics of earthquakes, and he was with NASA. So, it's not like they're all closed-minded people, but I think when it comes to what's presented to the public, there's this filtering that's done, and I guess that makes sense, but it's kind of just, we're going to show the things that we're the most certain about, I guess, but some of the things that are presented that they're the most certain about, I'm like, I'm just not so sure about that. Just because a lot of people in the room are saying the same thing doesn't mean they're all right.
Right.
I've seen that play out so many times in history. So
yeah,
there's a lot of really cool things though that come out of NASA, that come out of NOAA. A lot of amazing people that work there, USGS. So like, it's just that these organizations kind of grab a lot of these people, and I see things becoming more decentralized in the 21st century. So I think we'll see more people chart their own course and do their own independent research. And
yeah, but it can lead. The problem with that too is it can lead in the opposite direction, where it's like nothing that the science and like the academic science or these whatever you want to call them, so-called gatekeepers say is true. Like everything they say is a lie, and everything's a cover up, and everything's a conspiracy, and everything is not what it seems. And it's like it just becomes this crazy cult type mentality that people have.
Yeah,
especially online.
Tell me about it, bro. That's why psychology. I mean, I'm not a psychologist, but you have to learn a little bit about it because you just see it play out in front of you. And if you want to not be, I don't know, if you don't want to be a sheep, you got to kind of spend a little bit of time in all these different things and to learn about them. Because it's important. And you see,
well, it's crazy. I mean, just to use a recent example of that. 3-eye atlas, it was like, you saw like incredible division online of what this thing could have been. You had either it was a space alien spaceship coming from, some other star system, or it's just a comet, right? Like there's no in between there. And, that was crazy to me. because the guy Avi Loeb, the astrophysicist who was trying to claim that was some sort of like spaceship with like an anti-tail, whatever. Because he is like a Harvard astrophysicist and he's almost like part of the establishment. Like we just can't trust him because he's for what we automatically just it's become this game of questioning people's motives instead of actually interpreting the data and attacking the substance of what is happening. And when you're just reading stuff online or like watching YouTube videos and you don't really have the time to like look at this stuff and like look at the raw data and come to some sort of conclusion, it's like, all you can do is just rely on other people's interpretations of stuff. And oftentimes you're going to get that wrong. And these people are going to get stuff wrong too.
I don't know how familiar you are with the Schumann resonances, maybe a little bit.
Not super.
Yeah, they're these resonant energy fields that exist on Earth that are generated through lightning strikes, primarily. There's like 50 every second or so around the world. Mm-hmm. And they produce energy across the entire light spectrum, sometimes even gamma rays. So like a super bolt, it'll be so strong it can produce gamma radiation. But of course, we see the visible light when we see a lightning strike. So it's producing visible light. If you get close enough to one, you could feel the heat from it. That's infrared, the thermal. Mm-hmm. It produces ultraviolet, extreme ultraviolet, X-ray, but those quickly get absorbed into the atmosphere because they're very high frequency. But it also produces radio microwave frequencies. So you can pick that up, and when there's a big thunderstorm overhead, that can kind of scramble the lower frequencies in the radio microwave band. But the frequencies going from 0 to 50 hertz are such a low frequency that they don't get absorbed easily into the atmosphere or even into the ocean or the surface. Mm-hmm. So they form these standing waves. And specifically, 7.8 hertz is approximately the frequency and therefore the wavelength of the circumference of the Earth. Because the Earth's circumference is 40,000 kilometers. And you take the speed of light, which is 300,000 kilometers per second, you get 7.5 hertz as the frequency. And what we see is that at about 7.8 hertz, ranges from 7.2 to 8.5, 8.6 or so. But at that frequency, we see an elevation in power as compared to all the nearby frequencies, let's say like 6 hertz or 10 hertz. Those aren't elevated in power, but 7.8 hertz is, and it's consistently elevated in power. Then 14 hertz is a second mode, so a higher frequency. It's also harmonic with the Earth. Not as much power as the first mode, the foundational, but still elevated over normal. Then mode 3, 4, 5. That's the same architecture frequency as our brainwaves, which I touched on at the very beginning, and they have the same strength. So Schumann resonances are measured in the picotesla range, which is very, very, very minute. It's a 1,000th of a nanotesla. And Earth's magnetic field is like, 23,000 to 67,000 nanotesla. So these are extremely minor variations. But when we measure brain waves, they also come in at the exact same range in picoteslas. So if you have the same strength and frequency, that means there can be resonance between them. Because if one was stronger than the other, though the same frequency, then one would be considered noise and the other would be considered signal. So if the Schumann resonances were 10 times weaker than brain waves, maybe there's a mechanism to extract information from that, but the signal of our brain waves would be 10 times stronger. So it'd be difficult to get any data out of that. But if they're exactly the same strength and frequency, then the brain could theoretically grab information from the Schumann resonances because energy is information. There's always information encoded into any energy waveform. So if we have this natural resonance with the Earth that we evolved with, it's probably going back to our evolution. It's kind of a pretty deep thing, but that could then perhaps be an explanation for this dissemination of ideas that pop up all at the same time. Because if one person figures something out, and they're thinking about this, and maybe that just permeates into the Schumann resonances, and then it's the speed of light. So 8 times per second, this thing's pulsing for the foundational mode. Then someone in South America, the other person's in Asia, it could happen maybe the same day. All of a sudden, like they just get hit with an idea. Everyone's had that experience. Where they just get hit with an idea and it doesn't feel like yours.
Right.
It just feels like external, like whoa, okay.
Yeah.
Especially if you do any sort of like psychedelic, then you really explore into these fields and you realize that, consciousness is a lot more open and expanded than we think it is.
Is this like a different approach to morphic resonance, like Rupert Sheldrake's idea? Is this like was he talking about the
Yeah, it's all this would be the actual, like you could say, electromagnetic layer that could explain that.
I see.
Morphic resonance would exist across like basically everything.
the universe?
Yeah, I mean, at a consciousness level, at an electromagnetic level, a whole bunch of things. But this would be a specific subset that could help explain this.
Right.
But they've done experiments tracking the Schumann resonances in the Earth environment, and then also someone's brainwaves at the same time. And they found time periods where they entered into coherence with each other, because they can look at the frequency, the phase, and see, okay, we have coherence for 1 second or 5 seconds. And the research in general is that what they call an atom of thought, which is like the base smallest unit of like a thought. It's like a quanta of thought, I guess. It measures to like 100, 200, 400 milliseconds, something like that.
Yeah.
And so if you're able to enter into coherence with the Schumann resonances for just a few seconds, you could have perhaps a few thoughts like pop into your brain that maybe were stored in the Earth resonant field. That's not just from us, but from all life. And there's more to it than that as well.
How do we measure this and study this?
The Schumann resonances?
Yeah,
or
like if this idea that these ideas can be stored in this specific resonance and the human brain be able to pick it up simultaneously on opposite ends of the Earth.
Yeah, that would be...
Has anyone ever tried that?
Not exactly like that, but there has been a lot of work adjacent to that. There's been work looking at people's like biosignatures, and then what happens to Schumann resonances, and then like a solar storm impact, and seeing how that affects their heart and their brain waves and everything, which is kind of related, but not exactly. But for that, I guess you would need a good enough receiver and a good enough transmitter. So I would think that, and you'd probably need a big sample size of multiple times. So maybe like some mass meditation event of thousands of people in India, let's say, focusing on one idea.
Right.
And then a receiving group in meditation in South America, let's say, trying to receive that and then doing that over and over and over to see maybe if they can pull in the information. There's probably a more elegant experimental design that you can make, but just off the top of my head, I don't know. It's kind of it connects into these esoteric realms of how do you like measure this stuff?
Exactly.
There's enough data there to point to something that's interesting, but then in terms of like, how can we prove it? Is this in a field that's beyond our ability to prove empirically? Like, is this just too right brain to do that?
Right. Well, I mean, a lot of this type of stuff that you're talking about, you can't really use the scientific method to figure it out, right? Like it doesn't pass scientific method muster, these kinds of ideas. Yeah.
I think we'll look back in like 500 years and we'll see the scientific method and the scientific revolution as a really cool thing, but just as a stepping stone to one new, more integrated approach.
Yeah. Which is, that's a wild thing too, is like the foundation of the scientific method hasn't really evolved much, right? Like everything is just kind of like floats on top of that. And we haven't really like adapted that foundation very much. We've stuck to that rigid foundation, and I feel like it has to evolve.
We know it's not 100% correct because when the scientific method and the consensus right now is that consciousness is just an epiphenomenon that just manifests somehow in the human brain and basically nowhere else, then it's like, okay, guys, like this is nonsense. So there's a whole bunch, like the Big Bang is another example of that.
Yes.
It's just guys, there's more to this. Like consciousness isn't, if we're the only conscious beings in the universe and then everything else is not conscious and just completely materialistic and doesn't matter, then what does that say about us?
Right.
Like everything except us is not conscious. But it makes us puny in comparison because we're basically a speck of nothing in the vastness of the universe. So there's just some problems with the scientific foundation. I think we'll look at it in the future as one tool of many to use. And I think the science of the future is going to be more a science of consciousness exploration. But how is that going to be done? And, you know, what methods actually turn out to be like verifiable across time?
Yeah.
I'm not sure, like remote viewing is that.
Yeah, definitely falls into that category.
There's remote viewing. It's all the 4 million draconians on 3i Atlas. So
Remote viewing found that?
yeah, that's what some people said. Like, I'm seeing 4,000.
Oh my God.
4 million draconians. So there's a lot of just nonsense
There's
out there.
just so much nonsense.
But
And there's
there's-
so many charlatans out there, man.